Hello, and welcome back to the web series Developing SPECTER using Innoslate's digital thread. My name is Mallory Jones, and I'm a systems engineer here at Spec Innovations. In the previous videos, I introduced the Break the Ice Challenge, initiated the Lunar Rover project, and demonstrated the first half of Task 1, Research. In this fifth video of the web series, I will demonstrate the design and work conducted during Task 1 of the Lunar Rover project. This task was crucial for selecting a prototype to represent the needs of the Lunar Rover system. As mentioned in the previous video, during Task 1 Research and Design, the Lunar Rover prototype, Innoslate's documents and diagrams views, modeling and simulation, and CAD viewer were utilized throughout the following processes. In the Systems Engineering V model, this work took place during the architecture development and system design phases. The Task 1 statement of work was broken down into 3 subtasks: research, design, and incorporate Innoslate's digital thread. From this task, a set of requirements, bill of materials, and final report were produced. For the purpose of this web series, Task 1 was split into 2 short videos, the previously demonstrated research and now to be presented design. Once a system boundary and context were set and initial requirements defined, a final pass of research was executed to discover and compare existing rover prototype designs feasible for the mission scenario. This was done because the spec team determined it would be more schedule and cost efficient to purchase an existing rover prototype than to hire a subject matter expert to develop a rover prototype from scratch. During this prototype research, specific items such as functional capabilities and constraints, costs, and power usage were captured in Innoslate's digital database for each discovered rover prototype. The possible lunar rover prototype designs found were NASA's JPL rover, Kel Idea's LEO rover, and Robot Shop's PyCar. A comparison between the selected prototype designs was then conducted by analyzing their functionality, cost, and time to build with respect to one another. A checklist was used to compare the rover design's functionality. This was done by downloading a .csv output of the functional requirements, adding a column to the CSV per each prototype design, then checking if each functional element was determined possible or impossible for the 3 prototype designs. A functional score was then calculated by adding together the number of functional requirements met for each rover prototype design. The JPL rover met 25 of 47 requirements, LEO met 27 of 47, and PyCar met 21 of 47 functional requirements. In order to select the best prototype design for the Lunar Rover project, an analytical hierarchy process, or AHP, was conducted. This process involved determining criteria categories to score the designs against, assigning weights to each criterion based on importance of the project, and calculating an AHP score for each design. 5 categories were chosen and ordered as follows for the AHP analysis: maximum battery lifetime, maximum carrying capacity, maximum communication range, minimum labor hours needed for assembly, and lastly, maximum camera resolution. Once the rover prototypes were evaluated against each criterion, the scores were weighed and combined to calculate a total prototype score. Using these AHP procedures and the total functional requirements met, the LEO rover prototype was selected to be purchased for the Lunar Rover project. A bill of materials, or BOM, was then created as a list of equipment, tools, and additional materials that must be purchased to begin building the Lunar Rover prototype. This was done by decomposing the Lunar Rover system asset and the additional tools asset created in the asset hierarchy chart from the 3rd web series video, Cost and Risk Analysis. These asset entities held information such as manufacturer, serial numbers, and quantity. The purchase and delivery of the bill of materials was tracked using a Kanban board. In Innoslate, this was done by going to Charts View, selecting the Kanban board, and choosing to start with a blank board. Once the Kanban board was generated using the parent task, columns were added to the blank board to represent the various phases of the material acquisition, including to be acquired, purchased, shipped, and delivered. A task was then created for each material or equipment needed to be obtained for the Lunar Rover prototype, and was placed in the first column to be acquired. These tasks held information such as purchase orders, tracking numbers, and delivery signatures. A perform by performs relationship was then added to trace the acquisition task back to the asset entity. This allowed for easy tracking of the bill of materials. In addition to the LEO rover prototype, this bill of materials also included subsystems needed to fill the missing functionality gaps not addressed by the LEO rover. An excavation subsystem and storage subsystem were researched and decided to be attached to the body of the LEO rover. These subsystems required a 3D printer and robotic arm to be purchased, as well as LED lights and a LiDAR for enhanced navigation on the surface of the moon. As mentioned previously in the cost and risk analysis web series video, a cost breakdown structure was created to contain the costs incurred by the lunar rover project. At the start of this project, the CBS only included the costs incurred by the labor. But then in this task, the cost of each item and the bill of materials were also added to the breakdown structure. The tools, equipment, and additional materials were added to decompose the hardware costs in the CBS. In Innoslate, to estimate the total cost of the bill of materials, the top entity hardware cost was rolled up to add together every cost from the bottom up. These cost entities were also traced back to the asset entities created for the bill of materials using the incurred by incurred relationships. The final prototype design for SPEC's lunar rover project combined the LEO rover prototype with the excavation subsystem, storage subsystem, and additional navigation equipment. Innoslate's CAD viewer was used to store CAD designs of this final lunar rover prototype design. This was done by creating the CAD file in a preferred design software and uploading the file to an artifact entity in Innoslate's database. The image provided here is shown by selecting to view the uploaded CAD file directly in Innoslate. The final prototype design included the LEO rover prototype as the rover body, a robotic arm and 3D printed excavation claw for collecting regolith, a 3D printed storage container for storing regolith, 4 3D printed tire fenders to protect the rover body from dust abrasion, additional LEDs for enhanced visuals, and a LiDAR sensor for improved navigation on the lunar surface. The as-is system architecture created in the previous Task 1 Research web series video was updated by adding an asset for the lunar rover prototype. The lunar rover system connects the external systems together to complete the regolith excavation and water extraction processes for supporting life on the moon. Using the site locations and distance specifications defined by the Break the Ice Challenge, a travel route was mapped for the rover to follow during its mission on the moon. This route supports the mission scenario designed in the previous Task 1 Research web series video by commanding the rover to follow a path from the excavation site to the water extraction plant, to the delivery site, and then back to the excavation site for a continuous loop. The distances between the sites as provided by the Break the Ice Challenge are how far the full-size rover will travel during its mission on the moon. For the purpose of the lunar rover project and eventually testing the prototype, distances were scaled down to the prototype size. This was done by determining the scale between the maximum speed of a full-size operational rover from the Apollo program and the maximum speed of the LEO rover prototype. A scale of 3.33 meters per second to 2.67 meters per second, or 1 to 8.325, was calculated. Using this scale, the red arrow travel route was determined. Testing this route will be demonstrated later in another web series video. An excavation scenario was also created to model the excavation process the rover will follow each time it navigates to the excavation site on the lunar surface. This process is actually one portion of the mission scenario described previously in Task 1 Research web series video. At this step in the lunar rover project, this action diagram only describes the various processes and functions the rover will execute during its mission. However, once the lunar rover prototype is built and tested, a performance analysis was conducted to input performance parameters into this model. Then Innoslate simulators were used to calculate the amount of regolith the rover can excavate per excavation cycle and for the entire rover mission. This will also be demonstrated in a later video. Up next in the web series Developing SPECTER using Innoslate's digital thread is a video demonstrating Task 2 build. Thank you again for being here today, and I'll see you in the next video.